Welcome to the Thoughtful Software Podcast. Innovate and thrive with thoughtful software. This podcast is all about helping technology leaders simplify innovation, build emerging tech, and confidently fuel digital initiatives. Join Andrew Wolf and Fahad Shokat as they discuss how to navigate the ever-changing software landscape. Keep it simple, focus on people, and consistently deliver value.
All right, Andrew, let's talk about quantum computing today. I'm actually quite excited. This is a very interesting topic. Just a little quick background. I'm not a quantum computing expert, but what I do know is that today classic computers usually have bits that are defined by either a 1 or a 0. So think of like an on-off switch. And it's amazing that this very simple concept of what we can do today, we have the internet, cloud, gaming. It's pretty impressive. However, there are some limitations as our needs and requirements become more complex. We need more processing power. We need to use less energy. There's just so much out there. But so here comes quantum computers. So it's really interesting. And it's not intended to, from what I can understand, not to replace classic computers, because obviously we won't have a quantum computer on our desktops anytime soon. But it'll be like a different tool to look at more advanced and complex problems. Today, the problem, though, is that quantum computers are tremendously complex. And instead of like ones and zeros, it can be any kind of bit. I think they're called quantum bits, qubits. And I'm not going to go into it because I don't understand the physics behind it. But the end result is that it can store an enormous amount of information and use less energy. So imagine these are now computers that are going to be 1,000,000 times faster than today's computers. It's very difficult to predict how quantum computers will change the world, but imagine a computer that's 1,000,000 times faster, what we could do with that. So that's kind of what we're going to talk about today and how it might impact, how we do business, medicine, space exploration, security. And it's no surprise to see some of the biggest companies like Google and IBM and governments working on quantum computing. So Andrew, what excites you most about quantum computing?
A lot. When you talk about qubits, just so you know, I think state of the art is 57 qubits. For the reference, there are almost trillions of transistors on a typical microprocessor that you'd buy from Intel or AMD. And each transistor represents a bit. And so you can imagine the difference in scale between a qubit and bits at the current moment. However, there's a whole set of computational problems that, given the third state of a qubit, the difference between a bit and a qubit is the extra state and the amount of information that can hold. The problem can be solved a million times faster. So, for example, it's theorized that RSA, which is a common algorithm for encryption, it can be solved in milliseconds instead of what right now would take hundreds of years to solve, which makes encryption on the internet and stuff like that safe. It can be solved in a trivial amount of time. And it's not just that, though. There is like a doomsday event of quantum computing and quantum supremacy in the encryption space happening. But and just for definition, because I think we're in a new realm for a lot of people, quantum supremacy is when a quantum computer can do a task better than a traditional computer. But it's not just there. It's machine learning. It's, like you said, life sciences. It's chemistry and biology, modeling cells and all these other things much better so that you can come up with much more quicker computations. For example, looking at viruses on a quantum computer could be a game changer in how we fight, say, HIV and cancer. And so it's exciting because it takes these things that are incredibly difficult and computationally expensive modern computing and makes them cheap, efficient, and extremely solvable. And those are some of the hardest problems in computing today.
Yeah, it's fascinating. If you think about qubits, right, it could be either classic computers are 1 or 0. A qubit could be both. And it's just fascinating. It's like almost like you're out of the end game and you're going into the quantum realm. And so it seems almost very far-fetched. But should technology leaders have a little side eye on this and be thinking about quantum computing, or is it just too early to even think about it?
Absolutely, I think you should be watching. Almost on the monthly, some new quantum supremacy is achieved. And there is no core Moore's law yet because there's been no breakthrough like there was on the transistor based silicon, but there will be one day, right? The idea that somehow this technology is going to stop evolving and there's not going to be some breakthrough like there was Moore's law or anything like that that allowed the Cambrian explosion of computing that we've seen today to happen in quantum, I think isn't supported by historical fact. And I think you have to be watching this because the day that happens, there could become a day when your field is entirely disrupted. If you're in pharmaceuticals right now and quantum supremacy is achieved in that field, you are now on a racing clock against every one of your competitors to leverage this to create new drugs much quicker than you could before. And that goes for life sciences, that goes for encryption and security companies, that goes for people that base the machine learning. Right now, people are saying everyone needs to be a machine learning, deep learning company. Quantum changes the game there, right? And so you have to be keeping an eye on this because if there is this explosion, this innovation moment in this field, and you aren't one of the first people there, you can lose because it's not just about enterprises, governments too, right? If you achieve quantum supremacy against encryption and you are the United States, that means you can spy on every piece of internet traffic on the world uninhibited. That's a game changer for military intelligence. In fact, it's almost like you obtained a nuke, right? Like with the first nuke, no one could do anything about it because it was such advanced and destructive technology. This has the same premise there. And that goes the same for whether you're the US government, the US military, or a life sciences company. You have to be watching this.
Yeah, I think it's also becoming more accessible as well. IBM, I think, started a cloud-based quantum computing back in 2016, and I was looking at it the other day. And it's pretty fascinating. Like, can you start running examples and algorithms just in the cloud? Amazon and Microsoft now have launched their own. It's free to use, by the way. We can link this, and it's very interesting. It's fascinating to play around. I've seen use cases where like researchers at Case Western actually used Microsoft's cloud computing quantum computer to improve the quality of MRI scans. Ford is using it to solve traffic congestion. So the applications and use cases are already there. So I think it's a good point that you should definitely be looking at it.
And there will always be a class of problems until there's not, right? So one of the challenges with quantum computing a lot of people don't know about is that heat in the process of quantum mechanics causes massive amounts of issues. So you have to run at near absolute zero temperatures. And for those that are familiar with it, that's 0 Kelvin. At 0 Kelvin, the idea is time stops because the law of thermodynamics no longer applies because there's zero energy in the process. Okay. You have to be running near there where the theoretical, there's no energy left to make quantum mechanics accurate. One of the reasons you're not getting a quantum computer in your desk is the cooling mechanisms to make quantum computing work are egregiously expensive, getting down to 0 Kelvin because it's relatively new technology to do it. But on the other side, to keep it there and control that amount of energy and dispersion and keep the heat off and keep it accurate, it's just not something you're going to get on your home. But as that limitation goes away, as science gets better there, as people that look at thermodynamics and everything else that make that more dynamic, but that computer gets better too. And so as the qubits increase, if we're able to expend the energy and control the energy and keep it accurate and all that other stuff, again, you're going to see people like Ford using it. And it's going to get more and more, like I said, as the more qubits happen, the better we can model different problems. And it's all about how many qubits do we have and how many qubits are theoretically needed to solve your problem. And you'd be shocked to know how few you need to solve some of these problems. I think it was you need, I don't know if this number is correct, so one of our listeners will have to fact check me. I think it's 750 qubits or maybe it's 7,500 qubits to break encryption, RSA encryption. We're at like 165. So it sounds like we're not that close, and you'd be right, but it's not even an order of magnitude away. And if it's a 7,500, then it's only one order of magnitude away. That kind of stuff, that's one technological leap. That's one type of innovation away from getting it. And I think it's going to come quicker than people think.
I know there's a lot of different applications that we'll get into, but if you're just an enterprise with a ton of data, what can quantum computing provide you that something like AWS or Google Cloud, like the traditional processors right now, could not? And you might investigate this further.
I don't think it's worth going that far yet. I think there will come a time when that becomes the right path to go. I don't think we're there yet. I think we're so nascent on the technology that if you're not just going to take it in-house and try to solve it all yourself, and that's going to require quantum engineers and everything else, then I don't think that it's worth doing that quite yet. But there will come a time when it is.
I'm wondering if there's going to be some more tangible use cases in the beginning here. I mean, like we mentioned a few use cases now, but for just the average consumer, I don't see that anytime soon. One of the things that absolutely fascinates me about this technology is the idea of a quantum internet that I was reading about, that it's going to be much more secure than what we have today. It'll be a completely different environment. It'll be virtually unhackable. So if you're getting some message from someone on, and you'll know that whether your connection's been hacked or disturbed. So, it'll be quite interesting. It'll be very fast. I don't know how this converges. Again, as in my intro, it's hard to predict how we're going to use it, but I feel there are going to be some really interesting applications. Just for the average, for most of us, I think it's very far though.
I think trends all go in the same direction. Like if we learn from history, we're at the punch card phase of it. If you don't remember at the beginning of computing, people would take their punch cards down to the local computer office and they'd run their programs at a local computer office and they'd buy time at these computers because they're so large you couldn't put them in your office. And I think we're there with quantum right now, right? We're at the stage where you go to your local cloud provider and you pay Amazon money to run a quantum. And then when it's not like that, and there's now business quantum computers that you can install in your own data centers and use them, it will lead to, okay, now everyone has quantum computers. Now we need to connect them. And now we need quantum internet. And I think that's how this is going to go. Because I think it is truly cost prohibitive right now. If you're not a computer company and you're not going to invest in the teams of people that you need to do this, then you need to go to your, like I said, cloud provider and do it. But that might not be true forever. And especially if you're doing a lot of quantum computing, you're going to want your own because it's going to get expensive, especially if a lot of people are competing for limited resources. And this seems like the kind of thing that would be limited at first and then explode. Again, there's components of a quantum computer that are incredibly expensive to use. And that's that. And I also think that there will come a time when people want quantum algorithms written for them. And how many people are going to pay for that? There's not enough people to write algorithms today. There's such a shortage of good computer scientists. I think now you're going to be looking at an even bigger shortage of quantum algorithm computer science people. It's going to be a pretty drastic paradigm shift as well.
It reminds me of like the early punch card days of computer programming. I wasn't born then, but still, you get in line and you program, you wait for your turn to do your punch cards or whatever. And now where quantum computing is at the same point, even on these cloud platforms, you have to wait in line for your, algorithm to be in the queue and process. And so you just better be really careful about what you're trying to do. So it's going to be very selective. And so I see you have to be careful, like the applications and the use cases. So it's definitely not there. But I'm curious, how do you think it'll change software development? You're a coder, you've been coding for a long time. How do you see that changing to what you do maybe day to day when this is out a little bit more?
I think about this every day. And the reason I think about it is it can only go one or two ways. First is it's going to fundamentally change everything. I'm going to relearn everything I've ever learned, and that is going to be that. And that could be true. The other side of it is we've gotten so good at a field of abstracting things. Like I do know linear algebra and I know calculus because I had to take it to get my master's in computer science and all that stuff. But I don't have to know that because TensorFlow exists. And I can use TensorFlow that abstracts all that calculus and linear algebra from me. So I can still use deep learning without having to know all the mathematics. And so my theory is that it'll go one or two ways. The first is everyone has to relearn everything they did, that if you're going to be a foundational engineer, systems engineer, you got to learn it. Or you're going to go the route of using the libraries everyone gives you. But I think the real value, if you're going to be an engineer in the future and you want to be fundamentally needed, you're going to want to be on the systems side, building those abstractions for the everyday developer and helping build the React Quantum and TensorFlow Quantum and all that stuff. Because I think that's immensely more valuable than the other side. And ultimately, the abstractions will probably be needed even when we have artificial intelligence. The people writing the framework on top of the frameworks probably will, not exist anymore. So, Fahad, do you have any Bitcoin or anything like Bitcoin, cryptocurrencies, anything like that?
I do have Bitcoin, and I'm curious. Do you think Bitcoin industry should be worried?
Absolutely, it's crypto. Once you have crypto thing, it's not even quantum safe crypto. There's a whole set of cryptography, as you mentioned, that would make the internet much more secure. A lot of our systems do not use quantum safe algorithms. I think it's like 95% of all systems don't use quantum safe algorithms. And right now, a lot of experts know it's not safe. They believe that the innovation will come slow enough that Bitcoin and blockchain and stuff will be able to switch over to these quantum safe algorithms. But there is a doomsday scenario there where one day you wake up and the quantum computer is able to basically create any of the existing hashes or results for Bitcoin. And when that happens, basically you've created the philosopher's stone, right? If you're not familiar with that, it was something alchemists in the 1500s were obsessed with, of basically turning lead into gold, which would make gold worthless, obviously, if you could do that. This is the same thing. Basically, you're saying this finite store of value can be basically recreated with a quantum computer, and it's no longer a store of value if you can spoof everyone else's Bitcoin and just create many more types of Bitcoin. Or worst case, even if you can't create new Bitcoin, who's to say I don't have a valid claim to this Bitcoin? And so I think the systems we have right now are not secure enough to handle that. And I think it cause utter chaos. And at the end of the day, I think you really have to be worried about it. There are some like Ethereum 2.0 that started with this crypto quantum safe type mindset. And I think we'll see what the field does. If the field does it, then they're right long term. If not, I worry that one day people wake up and the store of value won't be there anymore and they'll have lost all their money. And again, it all depends on the speed of innovation versus the speed of keeping up. But I'll say if they get caught with their pants down, it's $1 trillion loss in the market, in my mind.
Yeah, I think there is some worry and concern for me as well. Because one thing I noticed when you're switching to Ethereum 2.0 or whenever that comes out, essentially all your Ethereum's locked up. And the assumption there is it's going to work, and all of a sudden, poof, your Ether's available and your Bitcoin's available, and somehow it's going to magically work with today's architecture. That's one thought about it. But even if I'm on the development side and I'm developing quantum technology, would you even want anybody to know that you can break Bitcoin encryption? Would you not even say anything?
That's the great question. I think eventually a lot of fishy transactions would happen. And then when they occurred, it would
Well,
just
I guess
be,
the point there is there's going to be some room for shenanigans. And
oh,
I just think that
absolutely.
this transition
Absolutely.
is not as easy as people think it might be. It's going to be challenging.
No. And again, don't take my word for it. The crypto experts say it themselves, the people that are on the side of being worried in that community. This isn't someone that's, I can come off as a crypto hater sometimes. I'm sure many of the real big enthusiasts would call me a hater. But at the same time, it's not my money being lost, man. It's definitely There is identity fraud, but this, again, it comes too close to a store of value needs to have ownership. And quantum takes ownership away from that if I can spoof the coins. You no longer, I can be whoever I want to be because it's anonymous, right? Now, what it can't do is create new Bitcoin. So there's still a finite supply. But even if it's just a finite supply, spoof, like it, then it does increase the supply because then people can use the same Bitcoin multiple times. So really, there's, I don't know, I think at the very worst, it doesn't drop to zero, or the very best, it doesn't drop to zero, but it drops to an incredibly low valuation.
Let's touch on one thing that I brought up around interfacing with today's tech. In your experience, as you've seen, just like our modern architecture work with, I don't know, old architecture. I don't know if that's the right word, but when something like this comes out and it's pretty advanced, what are some thoughts around just how do you make it work with these classic computers? Is there good best practices just in general? As we've talked about data lakes and data mesh and just all these things are evolving. How should you think about your technology stack as new things come up like this?
I think it's best to create a roadmap of things that you know about, and then you start including things into your roadmap and think about things as whether you want to assess them, whether you want to pilot them, whether you want to fully roll them out, and whether you're just going to observe them. And when you think about it that way, you can create a idea of, hey, I really want to look at this particular technology, but I'm going to observe it. Like quantum's in the observe category. You can't really test anything with it yet, unless you're one of the 2 or 3 industries that it can help with at this point. So it's just observe. And then I think a real assessment can be done in probably 2 or 3 years for most people on whether or not your problem is potentially solvable. So maybe some sort of small R&D project to really prove it out. And once you've proven it out, I think you go into a category where you look at and you try to build something with it. Does this actually solve your problem? And when it does, then I think you can go full bore into it and say, yeah, absolutely, let's deploy this thing all out. Let's make it a standard at our company. And that's the way I look at it as CTO. And that's why I follow such a breadth of topics, even in like product and sales and marketing. I even keep up with that stuff because that has downstream effect into our field, whether we want it to or not. We're not working in isolation. And so you have to look at the entire landscape and see what everyone else is thinking. And so when Salesforce first came out and said, hey, we're going to try to put everything in one platform, still a terrible idea. Salesforce is Salesforce. And you have to keep up with that kind of stuff so that what your landscape is going to be too, especially when people start forcing Salesforce into the engineering landscape and the product landscape there and say, hey, we want to be able to do licensing in Salesforce. And you say, great, I have to build something in my product or talk to Salesforce. And that's a very common feature today in most products. So if you weren't keeping up with it, you might be late to the show of actually implementing something like that and lose a competitive advantage that could have been a pretty massive competitive advantage. And Quantum's no different in that way than Salesforce. Although it's a much bigger paradigm shift, it's the same concept. And that goes for data mesh or microservices when they were hot, new frameworks like Next.js. It can all go into the same bucket of how you think about this technology.
Yeah, I think it's also, just as a kind of a final thought, what I find exciting about what we do as technology is evolved, the emerging technologies have become easier to access and use and manipulate and run proof of concepts. I think before, in order to build anything, you needed to hire a bunch of engineers and really expensive. It's still expensive to hire a lot of engineers, but you have the cloud now that's available. You have things like TensorFlow, as you mentioned. We've mentioned cloud-based quantum computing. I think just over time, a lot of these emerging technologies will get easier and easier to access, and it'll allow companies to try smaller proof of concepts and not necessarily go out and invest in a bunch of researchers that know quantum computing. So it'll be a little bit more affordable for enterprises.
Yeah, and as you're looking at something like quantum, because that's what this podcast is looking like, I think as you observe it, it makes sense to actually probably dip your toe in a few times. Run a project on it. Let's say you have this machine learning thing you want to do. Try doing it in quantum one of these times, right? You have to prove the concept of machine learning anyways. Just make a component of that. Pull aside an additional 20, 30K on your machine learning thing and try it in quantum, right? And tie it into your daily work so you can see where it's at versus where it might need to be to meet your needs. And that's a good way of looking at it. And just like technology is evolving every day, your organization has to think about how it's going to evolve too. We talked about technical debt before, we talked about all that and how that is leverage, but it also can weigh you down because you have too much of it and prevent that evolution. This is the same way. If you have the kind of debt that comes with not always looking at innovation as something you need to continually do, you're going to be way back because you're going to fall behind because you didn't move anything from observe to assessing. And you have to kind of move things back and forth and not be shy about it. You're going to spend some money in R&D. That's okay. One, the US government gives you tax credits to do it. So I don't know, go do it. And second, it's worth it because you'll be so far ahead of your competition when it does become a reality. When quantum computing first gets quantum supremacy in your field, you'll already have people familiar with it. So you can hit the ground running while your competitors are now just hitting the assess phase. You're able to jump right into implementation and put it into a product and get first movers advantage on it and be knowledgeable. That's a powerful position to be in.
I actually had one more question for you. You're a gamer, Andrew, and just because this podcast is all opinions, what do you think if there's a future for quantum gaming and what that might look like?
Well, that's an interesting topic. Gaming tends to be about 10 years behind general computing. And just because it's you have to ship a console sometimes. I say that, but as we look at like online game streaming, like Xbox just announced a beta of their Xbox Live thing through a browser, and you'll be able to play like 150 different Xbox titles like Halo in your browser, which is mind blowing to me because remember when Halo used to be like Halo 2 was like state of the art, and now it plays in a fucking Chrome browser. The same thing though. I think as that becomes popular, as internet speeds increase across the world, as it becomes more accessible, I think quantum can only serve to better serve like the AI engines that power these games, the other parts of the experience. Will it change like graphics or anything? Graphic computing is basically all floating point computational math and linear algebra and stuff like that. So in that way, that's something that quantum's really good at. And yeah, so the graphics will get way better. Whether or not it's used to quantum's used for gaming right away, I don't know. It's hard to tell. But if it's 10 years behind, we have to first see quantum be adopted in the business and government space. And then I think you'll start seeing it being adopted in the gaming space. Where I think it could be truly disruptive is in the virtual reality, augmented reality space, where, yeah, everything is very computationally expensive at the moment.
Can you get like a real life we can do Ready Player One then finally. I'm waiting for that day.
As much as I want to pretend it's going to turn out that good, and I don't even know if you can define that as that good, I have low faith that anything like that will turn out even remotely good. Like, I just imagine, like, we don't even send people to prison anymore. We just put them in a VR headset and keep them trapped in their mind or something like that. Like, I just view all the ways it can go massively dystopian, and I say, you know what? Let's just remaster Halo 2 on Quantum and make Quantum Halo 2. And let's set that as the goal. It's hard to mess that up. Or just get really dope graphics on PCs and stuff.
Yeah, I think this is an exciting topic, and I hope the next time we talk about it, there'll be some major breakthroughs that we can discuss. So I'm excited.
I'm excited too. This is a true game changer, and it's going to make the world a much better place.
Thanks for listening. You can always connect with us at skiplist.com.